So good afternoon, Australia. My name is Vladik. Uh, I'm talking to you from the other side of the globe. I'm in Israel. Actually, it's 3:40 a.m. here. Well, I guess you already heard enough jokes about being jet lagged without leaving your home. Anyway, my cat just gave me that look of, what's wrong with you, human? Like even they love to to throw a party at this time of day, but they're like, no, not for us. Anyway, it's such an honor and pleasure for me to be back at NDC Sydney conference. The last time I NDC Sydney, it was 2 years ago. It was in-person conference. Back then, my experience of using domain-driven design and some of the mistakes we did at that point and what we had learned from that. Now, this session today is going to follow the same scheme, but today I'm going to talk about event-driven architecture. I begin a few words about myself. I work in our industry for over 20 years now. Almost half of these years, I'm working in various architecture-related roles, and I really love software architecture. I'm really fascinated by the topic of software design. I tend to disagree with a lot of opinions. I prefer to ask uncomfortable questions and look, into the essence of the things, why different practices are there, problems they're supposed to solve, and what are the context in which each pattern or each solution should be applied. And I want to talk about today the event-driven architecture. Now, this whole topic of event-driven architecture, and specifically the event pattern, is actually way too common nowadays. The events, they're like everywhere nowadays. We have event-driven architecture, we have event sourcing, and of course we have microservices. Many are calling for integrating microservices asynchronously through events as the default. However, this popularity came with many treat event-driven architecture as some kind of a magic sauce, as if you can take a monolith, pour some events over it, and domain-driven design, and of course, event. Of course, that's not true. This is not how things work. This pattern is not some kind, but it's just a tool. And as any tool, it can be used to create some great stuff, but it also has a dark side. You're going to pay a hell of a price for misusing or abusing it. Now, I have experience of doing both, misusing and abusing it. In the next 40 minutes, I want to share with you some stories about the troubles I got myself into by misusing event-driven architecture, how we got ourselves out of those troubles, and what I had learned the hard way from that experience. Now, the stories I'm going to share with you are based on my experience working for a company called Internovus. Fortunately for all of us, that company doesn't exist anymore, which means I am free to say whatever I want. So, event-driven architecture. I want to start with some basics. I want to make sure that all of us agree on what is architecture, what are the goals of software architecture, what are events, and how does event-driven architecture works? What are the requirements for that architectural pattern to be implemented correctly? Now, I will start with some theory, and the horror stories I'm going to share later are going to be based heavily on this theoretical part. And I want to start actually, by asking you a question. What is software architecture? And here on the Slack channel, it is open here in front of me, and I'd love to hear your opinion. What is software architecture? Come on, people, don't be shy. I'm gonna do all the talking. Your opinions. Well, in the meantime, while your answers are coming in, I'll share mine. So when we're pondering this question, usually this quote comes to mind. Oh, actually, I'm seeing answers here in the chat of WebEx. Let me open the chat. A system level design that specifies how different parts of a system interact. Awesome. That's a great insight. Yeah. Cool. If you have more opinions, feel free to share them. And also, by the way, I'm going to run through a lot of material in the next 4 minutes. So if you have any questions, if something is not clear, just ask your questions. Don't wait till the end. I'm from Israel. We're used to interrupting each other all the time, so that's okay. Oh, diagram boxes with errors. Yeah, I love that answer. Model of the code. High-level choices made that have large effect on the technical development of the system. Cool, yeah, we're going to talk about that aspect as well. Okay, so we have this quote right here. Architecture is about the important stuff, whatever that is. Now, I doubt someone would argue that software architecture is not important, right? Robust software architecture is crucial for the success not only of the software, but in many cases of the whole organization that the software system is supposed to serve. For example, at my previous workplace at that company, Internovus, when we just started, we had to make many architectural decisions. For example, whether we should use the self-managed servers or go to the cloud. And I'm talking to you about it, it was about over 10 years ago. So back then, that question wasn't trivial. We also had to decide which databases to choose, languages, frameworks, etc., etc. And of course, we had to align the systems architecture with its business domain, which was by itself quite puzzling for us back then. Now, all these decisions were hard and risky. A correct decision would move the business forward, while a wrong decision the system way harder to implement and to maintain both in the short and the long terms. So architectural decisions are not only important, but they are also hard and complex. Therefore, in my opinion, the goal of software architecture is to manage complexity of a system. And usually we manage this complexity, as you said here in the chat, by decomposing systems into sets of interconnected components, modules. These modules, they can appear at different levels. They can be methods, classes, namespaces, services, and even whole systems. But at whatever level they are, the underlying idea and the underlying principles are still the same. Proper modules make it easier to reason about the system as a whole and about each of its components individually. Now, just a second, I want to open the chat window. It closed for some reason for me. Okay, sorry. So on the architectural level, modularity reduces risk of the design decisions we are making. It limits the scope. Oh, sorry. What's going on here? My second device is okay. Yeah, cool. So on the architectural level, modularity reduces risk of the design decisions we're making to the scope of a specific module. For example, let's say we have a component which uses a relational database. Well, if for some reason one day we decide the database doesn't work anymore, well, we refactor it to work with a document store. And that change is going to affect that specific component itself and not the whole system. Now, another way to put it is modularity allows us to divide the complexity of the system into two types. The first type is local complexity. And local complexity is the complexity of a single component. And the easiest way to evaluate it, or to just explain this concept, is the heuristic of asking yourself, if you were to introduce a junior team member and you need to explain what a specific model is in charge of, how hard or how easy would it be to explain what that module is doing? So, for example, in our system, in Internovus, we had a commissions module. All of its public API methods were a coherent set of actions related to calculations of commissions. On the other hand, we had another much larger module that was in charge of managing advertising campaigns, creative material, and even managing contracts with third-party companies. Now, the first module obviously has low local complexity, and the second one has a much higher local complexity. It would take definitely a while for someone to comprehend what was going on inside of such big module. And at some point of time, even I had no clue what was going on there, let alone junior team members. The second type of systems complexity is global complexity. And this one is defined by the level of interconnectedness between the system's components. With low interconnectedness, it is easier to understand what role each component plays in the system. It's also easier to evolve the system's components since the modifications in one module will have lower impact on the rest of the system. Here on this slide, you can see an example of a system with, let's say, relatively low global complexity. Now, we cannot give an objective score, give an integer value of how good or bad that architecture is, or how high its global complexity. But, we can compare this diagram to, here we have many more connections. This system is much more interconnected. As if we compare it to the previous one, this one has a much higher global complexity. These components are much more coupled to each other. And again, the overall system is way more interconnected and coupled. Boundaries reduce complexity of the system and make the system more adaptable to future requirements and changes. And that makes the process of defining boundaries a key architectural decision. So if back to the question of what is software architecture, in my opinion, Ruth Malan gave a crystal clear answer. She said that system design is inherently about boundaries. What's in, what's out, what spans, and what moves between. It reshapes what is outside just as it shapes what is inside. System design is about boundaries between components. And speaking about what moves between those boundaries of different this pattern we often use for decoupling events. And the idea behind this pattern is actually fairly simple. An event is a message which is used as a contract for integrating systems. Usually, that's what a typical event looks like. It has some metadata and the payload, which carries the message itself. Now, according to the contents of that payload, we can categorize events into three types. And I took these definitions from Martin Fowler's article, What Do You Mean by Event-Driven? So the first type of events is what Martin calls event notification. And such event is used to notify that something important has happened, but it contains minimal information on the nature of that change. If a subscriber needs more data, it can explicitly query the source system for further information. In a sense, event notification is like this weird thing right here. By the way, does anybody here doesn't know what the thing is? I'm looking at the chat now. Yes, that's pager. That's what Slack looked like in the last century. So yeah, how pagers used to work? You would receive this message which saying that hey, some stuff on, but you have to call the number on the message to get the detailed information. That's the idea of event notification. The system communicates that something has happened, but if other components need more information, they have to query explicitly for that. The next type Fowler calls event carried state transfer. And here the source system uses events to notify its subscribers about changes in that system's internal state, its data. And these kind of events can come in two forms. It can be either a complete snapshot of a modified entity, or the message can specify only the fields that were actually changed. So, for example, if you have a module which manages customers, and each customer record has, I know, hundreds of fields, and only one of them was changed, well, you don't want to dump the whole structure on the message box. So you can optimize that by only transmitting what has the field were actually changed because of some operation. In any way, all the data published by such events is sufficient for the subscribers to hold a local cache and to work with it. They don't have to query the publisher for any additional details, as in the case of event notification. And the final type is the events used in domain-driven design or for event sourcing. Usually we call them domain events. Such events are somewhere between the previous two types. As notification events, they notify that something important has happened, but they also carry enough data to describe what has actually happened. This data, however, it should be modeled as close as possible to the business domain and not some particular state representation, as in the case of events for carrying changes in state. Marian Duncan-Jones says here, domain event should be stateless as regards the entity to which event occurred. In other words, money deposit event holds no data on the account balance. In this case, account balance, that would be a state, a state representation of the account at this point of time. A domain event, on the other hand, describes what has happened in the business domain. Money was deposited. And with that, we want to transmit all the related information. For example, from which account the money was deposited, the destination, of course, the amount of money, timestamp, etc. Whatever we need, whatever we can add that describes that specific business event. So these are the three types of events. Again, notification event only signals that something has happened. Event carried state transfer is basically a data replication mechanism which is performed through events. And finally, domain events are somewhere in between notification events and event carried state transfer. And to demonstrate these differences furthermore, I love this example you can see on the slide here. Actually, I borrowed it from my friend, Ora Egozi, and she uses the following example to demonstrate the differences. So a notification event would be a marriage. Well, we are transmitting that a marriage has happened, but we are not carrying any other information about who married whom and any other related data. Event carried state transfer will say, hey, we have this person, and from now on, this person has a new last name. Well, maybe we would add a marital status as well as a field because it was changed as well. But that's it. We are not describing the details about the specific business event. Domain event, on the other hand, would look like, got married. And we have the ID of the person, the partner ID, and we have other information related to that event. For example, the person assumed their partner's last name, true or false. That would be a domain event. Now, it's crucial to choose the correct event type for a specific task. Otherwise, instead of a modern architecture, you will end up with accidental complexities and even the dreaded distributed monolith. And to demonstrate it, I want to share some stories of war and horror from my experience at that company, Internovus. Now, before I do, I want to briefly describe the business domain of that company so that it will be easier for you to understand the systems that we were building. So at Internovus, our goal was to allow companies that produce products or services to outsource their marketing-related chores, like creative materials for them, would publish advertising campaigns, optimize them, collect leads coming from these campaigns, and eventually our own sales agents would make the calls and sell our customers' products. Pretty complex and wide business domain. And as it usually happens, initially we try to implement this whole system as one big monolith. Complexity-wise, the system had very low global complexity. We only have one component. That's probably the minimal global complexity possible. However, these components' local complexity was huge. Well, everything was implemented in it, all that business logic. So unsurprisingly, after some time, this design started breaking under its own weight. It became slow, hard to test, and overall unpredictable. So we decided to break the monolith into two subsystems, marketing and CRM. That's what it looked like. Marketing system was in charge of collecting and publishing marketing events. For example, clicks, submitted leads, etc. And it was kind of stupid. It didn't really do anything with those events apart from publishing them to the subscribers. Those subscribers, on the other hand, they were free to do whatever they want with those events. However, as time passed, we noticed that despite that, all those subscribers were doing exactly the same thing. They transformed those marketing events into exactly the same state representation. Now, it's important to point out that this wasn't a mere projection that just transformed the incoming data. No, it calculated different business metrics for each event. For example, is this event coming from a new lead, or is this an existing customer that already purchased one of the products? And there were many such calculations. And not only that, some of them were really complex, but they also had to change frequently. They were highly volatile. And when that business logic had to change, it had to change simultaneously across all of those subscribers. Now, of course, that introduced a very strong coupling between all those systems. In addition, we were quickly hit in the face by unreliability of the network here on the left side of this diagram. Because we naively assumed that these events are going to be delivered exactly in the same order as they were published. And we also believe that they will be delivered exactly once. As if this whole system acts as one big logical transaction. As you may guess, that wasn't always the case. At the moment things didn't go as planned, the same events produced different results for different subscribers. Now, this we had to employ some infrastructural which entangled these components even more. Bottom line, the global complexity of that system skyrocketed. We solved this by refactoring that marketing system into an event-sourced system. That new implementation would encapsulate all that complex and volatile business logic. Instead of publishing mere notification events, you remember the first pagers, it emitted more elaborate domain events that described what has actually happened in the business domain. And this refactoring lowered both the global complexity of the whole system and the local complexities of its components. Well, because now we were making all those decisions in one place instead of duplicating them in BI, CRM, and all other subscribers. Now, speaking about that CRM system on the right here, originally we implemented it in a traditional way. It stored its data in a relational database. However, after some time, we understood that this implementation has been limiting us in multiple ways. First, it didn't scale. Second, the relational model limited the insights we were able to get from that data. Some business stakeholders needed more flexible ways of looking at that information. Therefore, we decided to refactor the CRM into an event sourcing and CQRS-based system. That's what our initial implementation of CQRS looked like. It was pretty much the client would submit a command, its execution would result in new domain events appended to the event store, and these domain events were used to project view models. Finally, the command's result was communicated from the read model back to the user. Those were the so-called one-way commands. But the thing is, there are no commands here. Those are just events operating as commands. A system of a command. And of course, it has to communicate back to the user the reason why it's used. Was there a technical issue, or that command was invalid? And if it wasn't valid, why? How the consumer can fix it? So in our case, because we tried to follow those one-way commands, the system's user experience was terrible. It was terrible because of this very long feedback loop. So to fix this, we refactor the commands to be executed synchronously. And not only synchronously, but the commands return their execution result directly to the user. The user didn't have to poll the projections for the updated view models. It was immediately returned synchronously. And this change dramatically improved the user experience of the whole system. Sorry. The users were getting the results of their immediately. And again, if a sales agent modified a customer by executing a command, they would receive the result of their action immediately. Now, the only limitation we had to follow here is that the data returned as a command result should come of a strongly consistent storage, the event store in this case. Why? Because projections, they are eventually consistent, and of course we cannot trust that they are going to be updated immediately. Therefore, if you need to return any information to the caller of a command and that information is available in a strongly consistent storage, go ahead, you can just return it. There is no need to go through that long feedback loop. Again, the change contributed to a much better user experience. Now, let's talk more about those projections. The CRM system published those domain events as its public API and expected other systems to leverage that freedom of generating their own projections. And at the beginning, it looked awesome, especially when we compare this to the initial relational database-based design. However, after our CQRS honeymoon period was over, we realized that, again, 90% of the subscribers are projecting exactly the same models. And again, as in the case of the marketing system, this introduced logical coupling. The logic that projected events into a workable state was duplicated in all those subscribing components. And not only was it duplicated, but it held the knowledge. Each domain event affects the state. It was tightly coupled to the CRM's implementation details. CRM exposed many different types of events, and all those subscribers had to closely follow the changes in the CRM's implementation. Of course, the CRM had to change often, and if a new event type was introduced, the subscribers had to reflect that change as fast as possible. Because, well, if a new event that was introduced in the CRM can affect the value of some projected fields here, ignoring the event would lead to inconsistent state. So, to sum it up, if we were to evaluate this architecture, well, it almost screams at us high global complexity. And we did. So to tackle this mess, we encapsulated that projection logic in the CRM system itself. Instead of exposing hundreds of domain events, it published changes to the projected state through event create state transfer. So basically, if we're speaking about those three types of events, we went from integrating through domain events to integrating through event create state transfer. Effectively, that change has compressed the CRM's public API and its implementation details, those numerous domain events, into a much more restricted set of public events. Public events that just describe the changes in the state. They were optimized for integrations with other systems. Now, of course, that change did raise the local complexity of the CRM system, but it wasn't a big deal, That change dramatically reduced the global complexity of the whole system. It did remove all the coupling we had here between these components. The next story is about a betrayal. So we had this nice microservices-based system in low global complexity and actually low local complexities of the service themselves. But then, because of some new requirements, we had introduced a new microservice. It processed data from all other services and communicated back some of its decisions. This solution looked, I don't know, it looked okay initially, but behind the scenes, what really happened here is that this new service ended up being an architectural Trojan horse. It introduced lots of implementation coupling, and because of that, the global complexity of that system went through the roof. The solution was to use domain-driven design's anti-corruption layer pattern. That pattern sits between two systems which are integrated with each other, and it acts as an adapter. It translates the integration model used by the original systems into a different model which is optimized for the integration needs. And that's what we did here. That anti-corruption layer in the middle, it separated the integration complexity between these services. It separated from the business complexity of the new service we had to introduce here. It was kind of complex, has very complex business logic. Now, ACL's local complexity was really low. Again, all it had to do is to aggregate data, transform it into a different model, and communicate it back to the message bus. But this more complex service ended up encapsulating the complexity of the business domain, and it wasn't coupled so much to the rest of the system anymore. Its implementation had to change frequently, but now it had much lower impact on the rest of the system. In other words, by introducing this thin translating service with really low global complexity, we reduced the with really low local complexity, we reduced the global complexity of the whole system. The story of the next system started pretty similarly to the previous one. Actually, it was our first step at implementing a microservices-based system. And back then, we've heard about the success stories of different companies using microservices, and that microservices hype was just starting. And we said, hey, microservices, that probably means that something should be small. Cool. So the smaller the service is going to be, the better the overall architecture. That was our. And let's see what results we got from implementing this naive logic. So we designed those services thinking that the smaller the service, the better. And of course, we're integrating them mainly asynchronously through publishing and subscribing to domain events. And initially, this design did produce low global complexity of the system and low local complexities of the components. However, over time, these services became more and more chatty. We started adding more and more connections between them, until at some point, almost all of them needed data from all other services. To provide the required data, we tried putting even more of that magic sauce, adding more and more events. But as you can see here in this diagram, the global complexity of that system skyrocketed. We ended up with a distributed monolith. And the abuse of the events was just a symptom here of the real problem. Sorry. The real problem is invalid decomposition of the system into modules. The solution, of course, was to merge some of those services together in such a way that would lower the global complexity of the system, and as a result, lower the number of events we had to transmit between the services in order for the whole system to work. Now, the last story, I cannot trash talk too much here because I wasn't involved directly in this implementation. So even though I have lots of emotions talking about it, I'll try and consider my words here. So about 3 or 4 years ago, Internovus was merged with another company. And here what I stumbled upon when we did architectural reviews. That system would process commands from its users, write some changes to a relational database, and events to a message bus. The goal of using the events here was to build a scalable distributed system. Now, please help me out in this chat right here. Do you see any problems with this design? Yes, yes. Katie and Michelle, you are both right. There's no guarantee that these events are going to be delivered if the database or the second or the message bus write fails. That's what I call transaction coupling. Transaction coupling between the database and the message bus. In other words, it's some kind of distributed transaction that should have been implemented. As you've said here in the chat, what's going to happen if that process, that system will, if it's going to die in the middle, just after committing the database transaction, but before publishing messages? Well, the user is going to get an error. Some of the data is going to be written to the database, and some of it is going to be lost because those events are not going to be published. Online data corruption. The system is going to end up in an incorrect state. Also, for all those subscribers here, the order of the events was important, but it wasn't enforced by the producer. And that's a different type of coupling. That's called temporal coupling. When these subscribers, they have to be called in a specific order. Now, let's see what the subscribers were doing with these events. So the first one, that backup DB here, it was simple. It just recorded all the messages in the persistent storage, as, storage mechanism for events. The second subscriber created a state representation of the business entity, and it stored it in an in-memory database as a cache. Subscriber, it forwarded events to BI for analysis, but first it enriched all incoming events with the state produced here in that cached state in the previous subscriber. Now, effectively, again, these two subscribers are temporally coupled to each other. They should be executed in a specific order, or otherwise, the analysis model, which is going to be communicated from the subscriber right here, is going to be enriched with inconsistent data. Now, of course, such orchestration of a distributed system is not trivial, and in case it just ended up corrupting our production data. Now, of course, the simplest solution to most of the problems here is the outbox pattern. Leverage the relational database, which was already there. And all we did is we expanded that original database transaction, in addition to committing the state changes, to writing the outgoing events into an outbox table. And then we used a relay to pick up those events from that new table and asynchronously to the message bus. That eliminated all that transactional coupling. Also, by writing those events into the same table, it was much easier for us to keep track of the events, the order in which they were written, and to check whether events are coming out of order in the subscribers. As for temporal coupling we had here in these two components, well, that was a result of bad service boundaries. What we did is we changed that second subscriber to publish event carried state transfer events with changes in the state of the data that were projected in that service, and those events were submitted to the BI systems. So these were the war stories I wanted to share. Now let's see what we had learned from that experience. And first, when designing event-driven systems, be pessimistic about it. Don't naively assume that things work. No, things will fail, and believe me, things are going to fail the most on weekends. I tested that assumption. It was correct. That optimistic consistency I show you here is nothing but eventual data corruption. And that term event-driven architecture, it contains the word driven for a reason. Your whole system depends on the delivery of its events. So make sure that the events are delivered consistently, no matter what happens. Next, identify your private and public events. Some events are implementation details, especially domain events in event source. It might be tempting to expose them as public interface. It's a part of your public interface, but you do not want external systems to depend on your implementation details, right? You want to be able to change those implementation details without breaking the integrations of the whole system. In other words, if you're going to expose your implementation details through the boundaries of the services, you're going to end up with and implementation couplings. So instead, leverage both private and public events. Private events, they can be very detailed domain events, and you can have many of them. However, when designing your public APIs, the boundaries of your components compress those private into a more restricted set of public events. These public events should be modeled with integration needs in mind. They should be optimized for integration. Your overarching goal here is to reduce global complexity of the whole system. And you can definitely do it by using both private and public events and making sure that your public events are as compressed as possible. Also, we saw that there are types of events. Use them all. Now, notification events and event carried state transfer are great for integrating services. And finally, instead of blindly integrating microservices asynchronously through events, evaluate their consistency requirements. If you've got services that can settle for eventual consistency, awesome. Integrate them asynchronously through events, probably using event carried state transfer. However, if one of the components expects to read the last write of the second component, You have two options here. First is to integrate them through a simple synchronous call to get the most up-to-date data. If, however, you need push-based integration, then that source service can raise a notification event, and the subscribers will react by getting the more detailed information through an explicit synchronous call, that pager pattern. If, on the other hand, both services share a set of methods that assume concurrent control, or in other words, only one method can be executed at the same time, stop right there. That's transaction coupling, and it will probably be safer to merge those components into into a single component. So these are the three lessons that I wanted to share, and that's time to wrap it all up. So quick summary: we spoke about event-driven architecture. We spoke about what is architecture, what are events, and what makes event-driven architecture work. So our goal is to manage complexity of the systems that we are designing, and we can do it through modularity. By dividing systems into components, we actually dividing the complexity into local complexity, which is on the and global complexity, the interconnectedness between the system's components. We saw that there are three types of events: notification event, which says that something interesting has happened; event carries state transfer for publishing changes in data, or we can say that that's a way of a replication through events; and events. Domain events are events that something interesting has happened in the business domain. The three lessons that, in my opinion, summarize our experience with all those troubles that we got ourselves into by doing event-driven architecture wrong. First, be pessimistic. Use both private and public events to compress boundaries of your components and to reduce the global complexity of the whole system. And finally, evaluate consistency. Because if you violate your consistency requirements by choosing an incorrect type of event, you're going to end up with a lot of pain. On that's what I wanted to share. A small shameless plug. About a year ago, I wrote this book. It's called What is Domain-Driven Design? It's a guide to this methodology that you can read over well, I was used to introduce it as a book you can read on a flight, but it's irrelevant nowadays. So I don't know, you can read it in an hour or an hour. It's a really short book about domain-driven design. Another book project I participated in is Domain-Driven Design, the First 15 Years. In it, I shared our experience of using domain-driven design in that company in Internovus. Currently, I'm working on another book. I cannot share any details, but you can follow me on Twitter or read my blog to get more details about it. And all I can say is the new book is going to be closely related to the subject of this discussion.